Hi everyone, welcome back to the Big O series. Today we're talking about another very common algorithm complexity, O of n, also called linear time complexity. In simple terms, O of n means the algorithm has to process each piece of data one by one. On a Big O chart, it looks like a straight line going up, showing that the number of operations grows in direct proportion to the size of the input. Let's start with a classic example. Imagine we have an array and we want to find the largest number in it. The most straightforward way is to take the first element as the current maximum, then check each number in the array one by one. If we find a larger number, we update the maximum. After scanning through the whole array, the maximum we end up with is the largest value. In this process, we have to look at every element. If the array has 10 items, we check 10 times. If it has 100 items, we check 100 times. The number of operations grows in direct proportion to the length of the array. That's a textbook example of O of n. For the second example, let's look at reversing a linked list. The idea is to start from the head of the list and gradually flip the direction of the pointers so the entire list ends up reversed. To do this, we use 3 pointers. One called prev, pointing to the previous node, one called current, pointing to the node we're working on, and a temporary next node to remember the next link. In each step, we redirect current.next to point back to prev, then move prev forward to current and move current to next node. Repeat this until we reach the end of the list and the list is fully reversed. Each node is visited once, so the time complexity is O of n. This is a great example showing that the number of operations scales directly with the number of nodes. From these examples, you can see that when we work with arrays, strings, or linked lists, basically linear data structures, many algorithms end up running in linear time. In fact, O of n is one of the most common complexities in everyday programming. For example, when calculating the total price of items in a shopping cart, we simply loop through each item and add up the prices. That's a typical O of n task. And in practice, as long as the input size isn't extremely large, O of n algorithms are usually very efficient, easy to understand, and straightforward to implement.